So you've wrapped up the analysis phase. You've talked to your stakeholders, you've managed to gather all the requirements, and now you have a massive pile of ideas, needs, and constraints. It is tempting to take that pile and immediately start writing database code. But jumping straight to the keyboard often results in duplicated data, logical dead ends, and a system that is difficult to maintain. That is why we rely on phase 2, design. This phase acts as a translation layer. It takes the abstract concepts from human users and converts them into the strict logic required by a database management system. To pull off that translation, database architects pass the initial requirements through 3 distinct stages of modeling. Each stage acts like a lens, bringing the data into sharper focus, moving from a high-level conceptual model to a detailed logical model, and finally to an exact physical model. If we skip these steps, we run the risk of building a database that ignores the client's actual goals, leading to systemic failure down the road. The first step in this translation is the conceptual model. Think of this as the low-resolution starting point of the design phase. At this stage, the goal is to map out the main ideas and systematize the overall processes. We present this high-level view to stakeholders to make sure everyone agrees on the basic shape of the data. Because it is meant for a broad audience, a conceptual model intentionally omits the granular, technical details needed to write the actual code. It serves as an early safeguard. By securing agreement on the business logic now, we prevent the team from spending hundreds of hours engineering an incorrect technical solution later. Once that big picture is approved, we increase the resolution and move to the logical model. This is where we create the structural blueprint for the database. To draw this blueprint, architects rely on a visual language called entity relationship modeling, often mapped out in an ERD. This diagram illustrates the building blocks of an ERD, which are called entities. An entity is a distinct person, concept, or object that we need to store data about, like a student, a delivery truck, or a specific product. To further define those entities, we add attributes. These are the specific properties belonging to the entity, like a student's ID number or their graduation year. Next, we establish cardinality. This defines the exact rules governing how these entities interact with each other. These relationships generally fall into 3 categories: one-to-one, one-to-many, or many-to-many. For instance, if a single student registers for multiple classes, the diagram visually tracks a one-to-many relationship branching from that student to their various courses. As client requirements grow more rigorous, architects handle complex data structures using an expanded framework known as an Enhanced Entity Relationship, or EER model. Drafting this logical model acts as a rigorous stress test. Forcing ideas into strict relational logic exposes flaws and missing dependencies well before any programming begins. Before we finalize that logical blueprint, the data undergoes a cleanup process known as normalization. Normalization enforces 2 key rules. First, it eliminates data redundancy, ensuring a piece of information is stored in only one place. Second, it guarantees that all related data dependencies are logical. With a normalized blueprint in hand, we dial into the final resolution, the physical model. This is where the design becomes a reality. The physical model specifies exactly what the objects will look like inside the software. It outlines the database tables, the individual columns, and the specific primary and foreign keys linking everything together. Applying full normalization ensures the database management system receives exact, unambiguous instructions. The resulting system handles real-world use without duplicating entries or crashing. We started with a chaotic pile of stakeholder demands and transformed it into a mapped, executable database structure ready for implementation. We achieved this by filtering the data through 3 increasing resolutions. The conceptual model established the big picture. The logical model mapped the ERD and normalized the data. And the physical model defined the tables and keys. This progression defines database design as a formal discipline of translation and structural organization. Mastering these precise modeling techniques is what an IT professional to architect the stable, scalable systems that businesses depend on to prevent data corruption and failure.